Yeah, it's very nice for me to present our work here. It's slightly off topic of this conference because I'm not going to talk about resource theory, but entropy. That's something also you can hear a lot of times in here. This yeah, I'm going on CQT, and this is the work with Dominic, Joseph, Francisco, and Valerio. So. The story started with von Neumann, who introduced the von Neumann entropy. This is defined for a state with a microstate probabilities. For a density operator, this is just a spectrum of that operator. It has some properties, and one property is it is invariant under unitary evolution. Microscopically, every evolution is reversible, so it is unitary. For example, the free expansion of gas. However, intuitively, in this case, the entropy should increase. So the phenomenon entropy is not characterizing this increase. So where is the problem? Well, von Neumann realized this is a problem with the observer. Because the observer is macroscopic, this will introduce some additional uncertainty to the state. And that's why von Neumann also introduced later the coarse-grained entropy or the macroscopic entropy. And with some slight generalizations, we arrive to the observational entropy. The observational entropy is defined with both the state and the measurement. The measurement is a characterization of the observer's coarse grain. And the value of this entropy is defined with statistics denoted as Py here, and also Vy, which we can call it's the volume of the QM atoms. And it's something characterizing the coarse graining, the granularity of what's coarse graining. With this definition, we can successfully separate entropy into two parts. The first part is an intrinsic uncertainty, which is simply the phenomenon entropy. The second part is additional uncertainty due to the coarse graining of the observer. Well, this is defined as the difference between the observation entropy and the phenomenon entropy. But we found that this value is always non-negative. So you can see this is an additional uncertainty due to the coarse graining. If the coarse graining is so good that it aligns with the eigenbasis of the state, then the observation entropy is equal to the phenomenon entropy because no further uncertainty is introduced by the observer. Yeah, so my work will focus on this observation entropy. We will do two different interpretations of OE, observation entropy. One is statistical efficiency. The other one is irreducibility. We find that in the classical case, these two values are always equal to each other. However, in the quantum case, these two values does not match. I will explain what is the quantum case later. And to solve this mismatch, we proposed a new definition of observation entropy that could connect these two together. So to begin with, let's just have a quick review of relative entropies. The classical relative entropy, or the KL divergence, is defined for two distributions, and it measures the statistical difference between two distributions. One quantum version of relative entropy is the omega p relative entropy. This is a generalization of the KL divergence for quantum, for density operators. And this is equal to the KL divergence when these two operators commute. The KL divergence, or the relative entropy, is a measure, it's a pseudo distance, in the sense that it is equal to 0 if and only if its two arguments are the same. So let's begin with our first interpretation. Suppose we have a state rho, and we want to compare it with another state, which we call the reference state. Here we choose the reference state as a uniform distribution, or in other words, a maximum mixed state. We can use a relative entropy to measure the difference between the state and the reference. However, from the observer's point of view, the observer cannot see the states directly, but see the states through a measurement, the coarse graining of the observer. What the observer sees is a measurement statistics of rho and u, and here represented as m rho and mu. The difference between these two states can be characterized with a KL divergence between these two probability distributions of these statistics. The first interpretation of observed entropy is that it can measure the statistical efficiency of this measurement. Well, by statistical efficiency, I mean the loss of distinguishability before and after the measurement between the state and the reference. So if we have a larger observation entropy, it means that the state and the reference are confused more after the measurement. Well, in formula, it is written here, and we can see that the statistical efficiency actually corresponds to the part that is the uncertainty due to the coarse graining. So for the second interpretation, I need to first introduce what is retrodiction. Retrodiction means to infer about the past or the cause of some effect. For example, we might want to know how did dinosaurs look like. Or a more simpler example is I get a negative result in a medical test, am I sick? To answer this question, we can model it as a stochastic process, where the input is whether I'm healthy or sick, and the output is the result of the medical test. And the medical test itself can be modeled as a conditional distribution PFY given X. We can observe the result, the output, negative or positive, but what we really want to know is whether I'm sick or not. To do this, we can use the Bayes rule. The Bayes rule brings for a given forward stochastic process, the Bayes rule gives us another process that is reverse in direction, and we call it the retrodiction process. And here is the formula, which is the Bayes formula. And in this Bayes rule, we need to pick a reference input distribution, which is denoted as PREF here. And this is a prior subjective belief of my input distribution, like my prior belief of how much probability I am sick or not, prior to knowing the results of the medical test. And there's another reference output distribution that can be computed from the reference input distribution. And with this, we get the retrodiction process, and for any given observed outcome PFY, we can compute with this formula an updated belief of the input X. So how can we use this in the quantum case? Well, let's consider the measurement as a classical process. We regard the state rho as a probabilistic derivation of these eigenstates. And the forward process is like this. We first pick X with a probability that is equal to the eigenvalue, and we prepare the corresponding eigenstate. We make a measurement on this state, and we observe measurement statistics. And this statistics is a conditional probability distribution, PFY given X. And its value is computed by the Boyle rule. We can also multiply the PFYX with the true input distribution lambda x, and then we can get input-output joint distribution. And we can apply the Bayes rule to this process and create a reverse process. The reverse process is going from the statistics to the underlying state. And we do this by taking using the Bayes rule, and here is the formula. Again, we need to pick a reference input distribution, which is denoted as gamma x here. Again, we can multiply this conditional reverse replication process with the observed output distribution, and we get a joint distribution of the input x and the output y. The second interpretation of observation entropy is simply the difference between this forward input-output relation and the reverse input-output relation. We can see that we call this irreproducibility in the sense that if this value is larger, then the forward and reverse process are more different. And it means that it is harder to replicate the underlying input. We have given two interpretations of the value of observational entropy, and they always match each other because they are basically derived from the same expression for OE. We observe that in both of these definitions, there is a reference appearing. First, this is the uniform distribution U, and the second one is also the uniform distribution. So a natural question is, since in the Bayes rule, there's actually no restriction on which reference prior we choose. Because the reference prior is actually a subjective choice. So we may want to replace this uniform prior with some more general prior, or most generally, some quantum state gamma that denotes our initial belief of the input rho. By this, we can define the observational entropy with a general quantum prior. So can this be done? Well, for the statistical efficiency part, it is easy because we can just replace this U with another quantum density matrix gamma. For the irreducibility part, well, we need to define the forward and reverse processor with a quantum reference, and this is not covered by the Bayes rule. So we need a quantum generalization of the Bayes prediction. The quantum Bayes rule we choose is the path map. Well, the path map for any given forward quantum process, the path map gives also a reverse process that is also a valid PDP map. We can say the path map is a generalization of the classical Bayes rule because it reduces to the Bayes rule when all the states and operators commute. I'd like to add that the path map is just one choice of the generalization of the Bayes rule to the quantum realm, and there can be other choices, but the path map has many good properties. So with the path map, we can define the irreducibility with a quantum prior. Here, gamma can be chosen as any quantum state instead of a uniform distribution. And here, QF, QR are the representations of the forward and the reverse processes. However, in this case, we find that these two interpretations no longer match each other. Well, it's not so surprising that they are not equal because they are derived from like two very different roots. However, we still want to see whether we can make them the same, because then we can make many things connected together, and that could also support our definition of our generalization of the OE to the quantum references. So the answer we found is this. We need to use another relational entropy, which is called the Belevkin-Stashevsky relational entropy, or BBS here. This is another generalization of the relational entropy to the quantum realm, and it is equal to the McAfee relational entropy if these two operators can meet. With this definition, we can obtain the forms of statistical deficiency and unpredictability, and they are equal. A slight modification is needed here for the irreducibility because here the TQF and PQR gamma are some other some other representations of the forward and reverse processes that are different from what we have in the previous slide. And yeah, more details in the full paper. This equality endorses our interrogation that the more the measurement confuses states, the harder it is to infer from the original state from the measurement statistics. Here is a comparison of the three quantities I introduced. The first two are using McAfee relational entropy with static deficiency and unpredictability. The third one is a BS relational entropy, and in this case, the two interpretations are equal, so there is only one line. We can see that in many cases, these values do not match each other. The horizontal axis denotes different values of the states rho and the reference gamma. In many cases, they do not match each other, but in some cases, they do match each other. For example, if the input state rho can be perfectly covered by the path requirement, then everything equals to the phenomenon entropy. And this means that the observer does not add any additional uncertainty to the state. Other case is if rho and gamma commute, well, there isn't a really very good explanation for this. Just in this case, things are slightly more classic. Okay, to summarize, we studied the observational entropy, and we give two different interpretations of it. One is statistical deficiency, the other one is unpredictability. We find that they are always equal in the classical case. However, in the quantum case, well, I mean, with general quantum priors, they may not be equal. We propose a new definition of observational entropy with general quantum priors to make these two interpretations match each other. A future direction is to consider not just a measurement by the observer, but a general quantum process. For a general quantum process, it is still possible to define the statistical deficiency and the unpredictability. And these things are actually related to some other topics. For example, the statistical deficiency can be used as a measure of performance of recurrent maps for general quantum processes. And the unpredictability actually has the same formula as the entropy production for classical processes. And probably as a generalization of unpredictability to the quantum case, maybe we can define some quantum generalization of entropy production. Also, in the definition of unpredictability, we use the representations of quantum processes that resembles the states over time. So it is left open whether we can connect all these things together. Okay, that's all my talk. Thank you for listening.
Okay, thank you very much. Do we have questions? Yes, we do.
Thanks for the interesting talk. I guess my queries is that it was reasonably clear how both this idea of coarse grading and this idea of this asymmetry between prediction and reproduction was defined and motivated in the classical definitions. Now, in the quantum definitions, I see mathematically what happened when we replace that prior with a quantum state. But I do not see the similar operational interpretation in the quantum regime. Can you comment on in what sense is, say, the quantum notion of it still some sort of like can be interpreted the same way as its classical counterpart? I mean, I see that mathematically it reduces to the Bayes theorem when the quantum state becomes classical, but to me, the Bayes theorem is very much a statement about our knowledge of a state, and that is intrinsically a classical thing. So when that prior becomes quantum, but since we can never fully describe a quantum state in our mind, what does it still carry a similar interpretation? Like, why do we expect these quantities to be the same? Why? I'm not surprised that they're different, and I'm not bothered by it. So, do you want to comment on? Do you still believe that quantum definition has the same operational meaning? And if so, how?
Well, first, the choice of quantum reference have appears in the definition of Pets maps. So we think it is a reasonable choice to choose this. And the second question, why we expect this to be equal? I mean, well, one reason is purely by the mathematical similarity of these two things. And the second reason is actually there isn't really, how to say, there isn't a unified definition of observation entropy with a general prior. So actually we do not know how to define this. So we want to have have a landing point. So we want to find something that has more properties. So maybe make these two things equal is quite a good property, such we can connect many more things together.
I see. Thank you.
I was wondering, like, you somehow switch from Yomigaki relative entropy to the Balestin Spessesky relative entropy, right?
Yes.
Does it have an operational interpretation, at least like classical limit, and like what, like why, or what does this tell us, right? We now use another entropy about the operational interpretation of the statistical definitions.
Well, the reason we choose this is just to make this equality actually. And for there are some interpretations of the BS relation entropy, but actually well, to be honest, we didn't use those interpretations and we just use the math. So. Yeah, there isn't really a good reason.
But I mean, it's clear that these two concepts should have some relation, right?
Yes.
The first is basically a measure of the irreversibility of a quantum process, my understanding is it's kind of the information erasure.
Yes.
And the second is sort of a difference between the difficulty of prediction and reproduction.
Yes.
So one would expect that in some sense these two things are correlated, but I feel like trying to make them completely equal by using certain mathematical definitions doesn't help my physical operational insight unless I know what they operationally mean in the first place.
Well, to making these two things equal may be just a coincidence. And this is the case we try to generalize this to general quantum processes. And in that case, it is hard to make things equal. And we think maybe we need to add some extra terms that kind of describes a non-commutativity or something. So
Yeah, I'm not familiar with this notion of relative entropy. Is there a good operational meaning to it? Like, is there life to standard relative entropy? Is there a notion of what it means?
I think we have to take these two.
Okay, let's take a look at the.
yeah.
Yeah, thanks again for the nice talk.